Welcome to Engineering Systems. Today, we're continuing our Availability Pattern series. Now, in our previous explainer, we explored single points of failure using our fictional food delivery platform, FoodDash, and we discovered something pretty alarming. Even though customers could open the app just fine and the web servers were humming along perfectly, the entire platform went completely dark the moment a single database server failed. That database was a classic single point of failure. But identifying that vulnerability is really just step one. The next, and frankly way more exciting challenge, is actually eliminating it.
So once we found a single point of failure, how do we get rid of it? How do modern tech giants, companies like Amazon, Netflix, Uber, Google, keep serving millions of users smoothly even when their servers, databases, and network components inevitably fail? Because make no mistake, in distributed systems, failure isn't a possibility, it's an absolute guarantee. Well, the answer to that begins with two fundamental concepts in availability engineering: redundancy and replication.
Here's our quick roadmap for today. First, we'll revisit the FoodDash outage. Second, we'll break down redundancy and replication. Third, we'll look at active-passive architecture. Fourth, active-active architecture. And fifth, we'll wrap up with the availability trade-off. Let's dive in.
All right, part one, the FoodDash outage, investigating the breakdown.
Think back to the root cause of that FoodDash outage. It wasn't that every single component in the cloud caught on fire. Nope, the problem was much simpler and, honestly, much more fragile. One single database server failed. But because literally every order, every payment, every login request, and every restaurant update depended entirely on that one specific box, its failure brought down the whole system. The blast radius was total. So, as the engineering team gathers in the post-mortem after the incident, they naturally ask a very logical question. Well, what if we just had another database?
Which brings us nicely to part two, redundancy and replication, the foundational concepts.
Let's start by looking at redundancy. Put simply, redundancy means introducing additional components so that the failure of any one piece doesn't immediately take down your entire system. Instead of one database, we deploy two. Instead of a single application server, we deploy a whole fleet of them. We might add redundant storage systems or wire up alternative network paths. The goal here is completely straightforward. Remove our dependency on any single piece of hardware.
But here's where a lot of engineers initially get tripped up. Just buying additional infrastructure does not automatically solve your problem. Imagine FoodDash deploys a second database server. Great, we now have two shiny database machines. But what if that second database contains absolutely no customer orders? What if it has no restaurant menus? What if it doesn't know a single thing about the active deliveries currently out on the road? At that point, if the primary fails, the backup database is practically useless to us. It's just an empty shell.
And this introduces our second vital concept, replication. Replication is the process of keeping multiple copies of your data perfectly synchronized across different systems. Think of it like this. Redundancy gives us the additional physical or virtual hardware, but replication gives those systems the actual information they need to take over when things go wrong. Without replication, redundancy provides very little value. And without redundancy, well, replication has nowhere to put its copies. These two concepts absolutely have to work together.
I love to think about it this way. Redundancy creates extra seats on the bus. Replication makes sure those seats are actually occupied. So returning to FoodDash, the engineering team decides to build a redundant database architecture. The primary database handles all the live production traffic, while a secondary database continuously receives replicated copies of everything in the background. Orders, restaurant info, payment records, the whole shebang. Now, every important piece of information exists in more than one location. If the primary fails, a perfect copy already exists and the business survives.
Okay, part three. Active-passive architecture, focusing on simple failover.
Let's see how this actually looks in a real-world scenario. Imagine FoodDash now has two database servers wired up in what we call an active-passive setup. Step one database is designated as active. All our customers, restaurants, and drivers interact only with this active box. Step two, the second database sits there as passive. It continuously receives replicated updates in the background, staying fully synced and ready at a moment's notice. And step three, when that active database inevitably fails, the passive database gets promoted, traffic is quickly redirected over to it, and the platform continues operating. It's an incredibly simple failover model because you have a very clear primary and a very clear backup.
However, there's a pretty obvious downside to that simplicity. You are dealing with idle infrastructure. That passive database spends the vast majority of its life just waiting around doing nothing. As an engineering team, you are paying top dollar for expensive database hardware that contributes absolutely zero capacity to your daily operations until a failure actually happens. It's literally like paying full price for a spare tire that takes up half the space in your trunk.
So, what's the alternative? Part 4. Active-active architecture, providing simultaneous capacity.
The shift in strategy here is massive. Instead of having one active database and one standby database, both machines actively participate. Both handle requests, both contribute compute capacity, and both serve production traffic simultaneously. Now, if one fails, the other one just immediately continues operating. There's no standby system that needs to be promoted. The remaining infrastructure simply absorbs the extra load, which gives us way better resource utilization and a much higher baseline of availability.
Which brings us to our final section, Part 5, the availability trade-off, complexity versus uptime.
When we compare these two architectures directly against each other, the trade-offs become glaringly obvious. Active-passive gives you a very simple failover process and far fewer synchronization headaches. Active-active, on the other hand, gives you fantastic resource utilization and much higher scalability, but it comes at the cost of massive synchronization complexity. Because in an active-active system, engineers now have to ensure data remains perfectly synchronized across multiple active systems that are all taking new writes at the exact same time. Conflicts are going to occur, coordination gets significantly harder.
Looking at these side by side really summarizes the engineering reality perfectly. There is simply no free lunch. The more resilient a system becomes, the more engineering effort is required to keep it running. For a lot of internal business apps, active-passive is great. It provides high availability with really low complexity. But for large-scale consumer platforms serving millions of users, active-active architectures become strictly necessary just to achieve that massive scale. It all ultimately comes down to your business requirements, your team's operational expertise, and of course, your budget.
Let's do a quick recap to lock in these architectural concepts. Single points of failure create massive outages. Redundancy removes our dependency on any one component. Replication is what actually protects our critical data. Active-passive architecture provides a straightforward, simple failover, and active-active increases both availability and scalability. Together, these principles form the absolute foundation of highly available engineering systems.
But, as is usually the case in engineering, solving one problem just reveals another. We've built this beautifully redundant, replicated system, but we are missing one absolutely critical piece. When a component fails, how does the system actually know it has failed? How does traffic automatically redirect a healthy infrastructure in a matter of milliseconds? Redundancy alone isn't enough. We need automatic detection, and that is exactly what we'll dive into in our next explainer on failover and health checks. Thank you for watching Engineering Systems. Be sure to subscribe so you don't miss the next step in our Availability Patterns series, and I'll see you in the next one.